This next segment of material is about the Poisson approximation to the binomial. There are certain circumstances in which the binomial distribution can be approximated by other probability distributions. And actually we will cover two, but at this point we will cover the Poisson approximation. This occurs, can happen if n, the number of trials in the binomial, is large, so that the number of realistic outcomes is small, and so that the n is a long way away from the number of outcomes that is reasonably can be expected, like 0, 1, and 2. You can think of this as to be 50 or 100 or even more. All right, it's not etched in stone. And if the average, which we'll put as mu here, for the binomial is less than or equal to 7. All right, both of these conditions must hold. Typical case is, say, with the that we have a batch of 1,000 parts, widgets, whatever, and the average defect rate supposed to be, let's say it is, 0.1%, which means 1 in 1,000. We could answer the question like, what is the probability of getting more than one defective part in a batch of 1,000. Okay. Well, in essence, this is a binomial because the maximum number of defects is 1,000. Now, it's never going to happen, just like we're never going to get 1,000 phone calls in a 5-minute period. But that's the theoretical. Alright, so it's a binomial. So written as a binomial, this is a probability of more than 1, x the number of defectives in this case. Well, let's do n first, since it's easy and we know it. We just wrote down n is 1,000. Then p, the probability that any one item is defective, is 1 in 1,000. 0.1%. Alright, and actually it's not incredibly difficult to do that with the binomial formula, but we're going to now look at the approximation. Oops, alright, too far. So, is the Poisson approximation applicable? Well, whenever you see n large, probability small, you should think about the Poisson. Okay, so two conditions. N in this case is 1,000, which is large. All right, if you want to, this is greater. If you want to limit, this is greater than 50. 2, the average of the binomial NP, 1,000 times 1 in 1,000 is 1, is less or equal to 7. So both conditions hold. So the Poisson can be used to approximate this binomial. Alright, what do we do? Well, we say that this is equal to the probability, or is approximately equal to the binomial, sorry, the Poisson probability x greater than 1, where the average is equal to the 1 that we just calculated. Okay, and at that point we have a Poisson problem. We'd get it by calculating the complement. Alright, so average of 1, find the probability that x is less or equal to 1. Average of 1 less or equal to 1 is 0.736. And so the answer to this question is 264. Alright, so that's how we can use the Poisson to approximate certain binomials where we have a large n and a very small p. Okay. Now let's look at this problem. Okay, again I suggest that you try this problem and then I'll look at my answer. Alright, in a city of 400,000 there are roughly 200 violent deaths per year. Violent deaths, we mean murders, manslaughter, auto accidents, industrial accidents, whatever. What is the probability of at least, we'll make that 2 violent deaths in a year in a high school of 400 students? Okay. So we have a situation where it's a discrete probability distribution. Number of violent deaths was 0, 1, 2, 3. Okay, is this a binomial or Poisson? Well, if you have 400 people, what's the maximum number of violent deaths you can have a year? Is it infinite? No, it's 400, right? So this is a binomial. It's a probability of at least 2, and the number in the group, possible number of maximum number of deaths, 400. What's the probability that any one person dies a violent death? Well, it's 200 out of 400,000. Okay, and that probability is very small, 0.005. Okay, so here we have a situation where the n is large, p small, so we're thinking Poisson approximation. So we will check for the Poisson approximation. So first, n in this case is 400, is large, greater than 50. Secondly, the average np for the particular binomial n, 400 times probability 0.005. Okay, and that's, if I've done everything correctly, that's 0.2. Okay, so Poisson approximation of this binomial is good. Or in other words, it'll be a reasonable estimation. Alright, so we get this binomial, translate this into a Poisson. This is approximately equal to the Poisson probability x greater than or equal to 2. The average is equal to, right, average for the binomial, 0.2. Alright, it's greater than or equal to, so we use the complement. It's 1 minus the probability x less or equal to 1. Average of 0.2. Well, let's go see if our tables can do that. Alright, 0.2 less or equal to 1. Yep, 0.2 is here, less or equal to 1 is 0.982. 0.018. Okay, actually, small probability. It's probably a bit higher than you expected. Okay, so the probability of 2 or more violent deaths in a year out of a group of 400 people is about 1.8%. Okay, and that's the binomial approximation, the Poisson approximation to the binomial.